do want to remind you that I think this second test is the most difficult of all the tests. So uh, maybe of the entire year. Maybe in the second semester, some of them are a little more difficult. But just, I don't want to scare you or anything, but you know, I want to scare you a little bit, right? So that you do well on it. So with projectile motion, you know, we talk about this sort of typical projectile motion problem where you have something, it follows this parabolic path as it goes through space. This is a parabola, by the way. And it's because of that, the dependence on y is that 1/2 at squared, right? A parabola is a quadratic function, and that's why it is a parabola. But the velocity vectors do a couple things. The velocity in the y direction starts out big, it gets smaller, it goes to 0, it gets bigger in the negative direction, like that, and then the velocity in the x direction goes like that. It's constant all the way throughout, and that's because ax is equal to 0 and ay is equal to -10 meters per second squared. So we treat this as two separate problems. One as a problem where it has 0 acceleration, and that's where we get this x equals vxt, right, which is just one of our kinematics equations, but with the acceleration equal to 0. And then we have this constant acceleration problem, which we did in chapter 2. Right, that was the sort of problem where we throw something up in the air and you to figure out how high it goes, what its velocity is, and all that business. Let's take some time and we'll work through some problems and sort of see the technique for working through these. Listen, they're all a little bit different. Uh, so there really only maybe, well, there are lots of different problems you could potentially see, but they all sort of use the same principles. So let's see, this is, every test has them. So, okay, the ball is rolled horizontally off a table with an initial speed of 0.24 meters per second. The stopwatch measures the ball's trajectory time from table to floor to be 0.3 seconds. What is the height of the table? This is a pretty easy problem because the ball comes off horizontal, and so that means that you're not going to have to worry about components of vectors, right? Because if it's at an angle, which you could also see a problem like that, and I'll work one, but if it's at an angle, you have to find the components of the vectors. Listen, I always like to draw a picture. This is what this object is doing. It's following this sort of parabolic path as it goes off the table. I know that the speed in the x direction is 0.24 meters per second. The reason that I know it's all in the x direction is this phrase right here. It's rolled horizontally off the table. That means it comes off and it's not at an angle. And also just there is no angle given. There's no mention of an angle. Right, so it's coming off straight off the table. However, immediately when it comes off the table, it starts picking up this y velocity that starts increasing in the negative direction. All right, then I can write down the things that I know. I know that Vx is 0.24. I know that t is 0.30 seconds. And I know that, well, that's all I really know. Well, actually, there are a couple other things that I know. I know that V naught in the y direction is what? Is 0, right? Because there's no y component. And then I also know the acceleration in the y direction is -10. If you want to write your equations, feel free. You can write them on your form, on the test, or whatever. These are just the kinematics equations, but they're, you know, adapted to the projectile motion. They look like this. And Vy equals V naught y plus AYT. We could get these for the x motion too, but the x motion, the acceleration term goes away here, and it goes away here. So we just left with really that displacement function. Um, so let's see, I want to know the height of the table. That means that I want to know y. I want to know what y equals. And y is really only present here, so I need to look at that. I always like to ask myself, how many knowns and how many unknowns do I have? I'll label the unknowns in red. That's unknown. See, this is 0. That whole term is 0. That's the only unknown that I have, so this is a really simple problem. It's just 1/2 times -10 times t squared. T is 0.30 seconds squared. That's 5 times 0.09 5 times 9? 45? Yeah, so it must be 0.44 meters. Nice little simple problem. You're gonna have, I think, 3 projectile motion calculation problems. It sort of depends how far we get into chapter 5. I don't think we're gonna get that far into chapter 5. So that means you'll have more space for projectile motion and stuff. Okay? Some will be easy like this one, some will be a little more difficult. Let's do one that's a little more difficult. Y'all okay with this one? I could do this right now if I gave it to you, just different type problem, but same idea. Okay, good. These are pretty easy, but let's look at one where you have to do the components. Can I get rid of this? All right. I think there was one on this test. Maybe not. Nope. This was fall 2012, by the way. Here's fall 11. Oh no, that one's. Let me go to exam 1 for fall 11. Okay. So did we work this problem last time? Do you remember? Let me pull up another exam just for a little variety. Let's do exam 2. Online version. Sorry. Okay, this one's very similar, but it's just different numbers. So, oh no, let's do this one. No, we'll do that one next. So we'll do 16 and 17. This is follow 9, by the way, exam 1. It says an archer shoots an arrow with an initial speed of 100 meters per second at an angle of 30 degrees from the horizontal. How high does the arrow travel? Draw my little picture. All right. Pretty good chance that you'll have a question like this. All right, this is sort of just your typical projectile motion problem. So basic, straightforward thing. So make sure that you can work this problem. If you can work this problem, you can probably work the others as well. I want to know what is the maximum height right here. I know that the initial speed is 100 meters per second. So this is 100 meters per second. And then I also know that this angle is 30 degrees. So you just want to go ahead, anytime I have my velocity like this, I just want to go ahead and find out what are my x and y components. V naught x is 100 cosine 30. I always get these mixed up. It's cosine 30. Yeah, cosine 30 is 8.86. So this is going to be 87 meters per second. And then V naught y is 100 sine of 30. And that's sine of 30 is a half, so that's equal to 50 meters per second. All right. My wife said that y'all are having difficulty. I'm not sure if it was y'all, but just sort of having difficulty thinking about vectors. Like we talked about the components of vectors in terms of displacement, and I think that y'all sort of got that your displacement vector is made up of x and y components. But that's true for any vector. That a velocity vector or a force vector can be broken down to its x and y components. So if I think about this vector that is 100 meters per second here, that's equivalent to saying that I have 2 vectors, one direction 87 and one direction 50. So it's just like we did in chapter 3 with vectors, but just now applied to velocity. All right, so I have my v naught x and v naught y. Then I want to do that little trick where I say at the top of the trajectory, vy is equal to 0. And then I can say vy at the top is equal to v naught y plus ay t top. Because you see, I don't have any time information, and anytime you don't have time information, you need to figure out some way to get that time information. And this is one of those ways. I think on the next one, oh no, the next one's showing. I'll give you an example of another way to find that time information as well. So a couple different variations. But in this case, I want to find the time at a particular point. I want to know the time right here because I'm looking at the y displacement there. So I want to know the time when it's at that point. All right, so Vy top is 0. That's equal to 50. minus 10 times t top. So t top is equal to 5 seconds. 50 minus 10 times 5 is equal to 0. Or the other way you'd solve this, almost always. I'll show you another example where that's not necessarily the case. All right. Actually, in the previous problem that we worked, I think you didn't see that one, did you? In the previous one, when you have a problem where something's coming off of a table like this, right, if you don't know the time there, it's not so much that you're getting t top, but you're taking your y displacement, and then you say that y is equal to v naught yt plus 1/2 ayt squared. V naught y in this case is 0, and then you solve that for t. That's just like you're dropping something, just finding the time that it takes to drop. Almost always consider the y motion when you're finding the time. This is one way of doing that. This is like that problem we worked where you throw something up and it comes back down. And then you can also do it this way, where like if you're dropping something, you take your y displacement, it's equal to 1/2 at squared, and just solve for t. Y'all did this in a lab. Oh, you're not in a lab though, are you? Yeah. So y'all did this. Y'all did the projectile motion lab. It was one of those that you did. All right. So now we know t top is 5 seconds. I want to know the height, and I just say y is equal to v naught y times t plus 1/2 ayt squared, and that's equal to well, v naught y is 50 times 5 seconds minus 5 times 25. That's 250 minus 125, 125. So D is the right answer. Notice here that sometimes you have to double that time, right? Like I got 5 seconds for T top, and I used 5 seconds here. The reason I did that is because I was looking for the position at this point, which I know occurs at T equal 5 seconds. But sometimes you'll want to know the position at this point, right, the X position, in which case you'll use what time? 10 seconds, okay? Let's look at one other problem, or one other, I don't know where one is, so I'm just going to show you, I'll make up one and show you, because there's one other sort of variation on how to find the time. Well, I could do it with this one, actually, since we already sort of have it laid out. Another set of information that I might give you is to say, what is the y displacement when the x displacement is, say, let me think about this for just a second. So at 10 seconds, it's going to be at 870. Let's say at 500 meters. If x is equal to 500 meters, what is the height? Let me write that in words. So if x equals 500 meters, so when the object is 500 meters from where it was launched, what is the height of the object? And this is a case where you'd use the x information to find the time. So I would just say x is equal to vxt. I have everything there. It's just going to be 500 meters, because that's the location that I want to know. Excuse me, right here. I want to know what is the y height at this point. So I want to know the time at that point, which is 500 meters from the original position. So 500 meters is equal to Vx, which is 87, times t. Divide both sides by 87. And I find that t is equal to 5.7 seconds, which makes sense because if it really is right here, this is 5 seconds, so I'm on the downside of that. So I have 5.7 seconds there. And if I want to know the y height, then I'm just solving this equation again. So I say y is equal to v naught y, which is 50, times 5.7 minus 5 times 5.7 squared. The minus 5, right, is 1/2 of negative 10. I just didn't write that out. I get 123. Well, let's think about that. So 123, look, I know that here it's at 125, so here it's at 123. It drops a little bit in that little bit of time. Okay? So that's another way you can find the time. If you're given the x range and you know the velocity, then you can find the time in this way. All right? Usually you use the y motion, but sometimes use the x. Depends on what you know. And then there's one other thing. We worked this in class, but I could also ask, what is the velocity, for example, at a particular point? So let's say, I'm going to erase this part right here, this in the black. If you look back at the old tests and stuff, you'll see this. So I could say, what is the velocity at x equal 500 meters? All right. So using the information that I had before, I know that the time is 5.7 seconds, right? Because that's what I found over here. And by the way, this wouldn't be all one problem. I'm sort of showing you 3 or 4 different problems. So you wouldn't have to do all these steps for one problem. We know that t is equal to 5.7 seconds. I know that Vx is equal to 87 meters per second. That doesn't change, but Vy does change. Vy is V naught y plus Ayt. V naught y is 50 minus 10 times 5.7 is equal to negative 7 meters per second, as it should be, right? Because if it's on this downside, the velocity vector is pointing down now. It's not pointing up anymore. It's going in the negative direction, its velocity. You with me, folks? Yeah. All right, so then if I wanted to know the net velocity, I have the x component, I have the y component. So to find the magnitude of that velocity, I would just do the square root of 87 squared plus 7 squared. The negative goes away. And then that's equal to 87.3. I'll write 87.3. Okay, so you should be able to find the velocity at any given point if you know the time at that point. You know Vx doesn't change, and then you just plug in your time to find Vy. Lots of different variations on that problem. I think those are sort of the big ones. All right, practice will help. You'll sort of get a feel for them. It'll feel easy to you. Does this seem easy? A little bit? Sort of, kind of? Alright, it's not that easy actually. It's not really at all. Okay, can I take this away? Alright, more projectile motion? Anything in particular? If not, I'm going to launch into 2D vectors, which are kind of difficult. People find that difficult. Alright, okay. Alright, let's remember sort of the idea behind working force problems. The first thing you want to do is label all the forces. The second thing that you want to do is assign a coordinate system. It'll be obvious in most cases what the coordinate system is. Up is positive, down is negative, but you get to pick that. Assign a coordinate system. Draw a free body diagram. Find the components of any forces not on the axis. So find x and y components. Apply Newton's second law. When you apply Newton's second law, you'll have 2 or more equations Then you just solve the equations. All right. That seems like a lot of steps, but it's not that bad, really. Let me show you a problem. I had a problem on a test once like this, so I'll just sort of recreate it here. Let's say that we have a block that is 10 kilograms. Okay, it's on the ground, and there's a guy that's pulling it with a force in this direction. We'll say this force is at 30 degrees, and let's say that he's pulling with 20 newtons of force. Okay? First of all, in the in-class section, we haven't talked about normal force. I think I sort of talked around normal force. Did we talk? Yeah, we did talk about normal force. Uh, maybe not. Anyway, if you have an object that's sitting on a surface, you have a force that's acting downward, the force weight, and then you have another force that counterbalances that. It's part of that sort of Newton's third law, action-reaction forces, that we call the normal force. Not normal as in like usual, but normal as in perpendicular. The normal force is always perpendicular to the surface. You have ever heard that definition of normal? It means perpendicular. Now you have, right? Okay, so this means perpendicular. So that normal force is always perpendicular. So for example, if we're on an inclined plane like this, and I have an object, the normal force then will be perpendicular to the surface. It's not going to be opposite the weight necessarily. But when it's on a flat surface, it is opposite the weight because of the way they're labeled. All right. So I need to label my forces on this. I've already labeled one force. It's the force that the guy's pulling on it with. And I want to know a couple of things about this. I want to know what is the normal force, and I also want to know how fast it's going. Right, this is like a guy, he's pulling the block. So it's accelerating in the direction that he's pulling it. And I want to know how fast it's doing that. So how many more forces do I have acting on this block? Or what's one of the forces that's acting on it? All right, I have the weight of the object. So I have Fw. Remember, Fw is equal to m times g. So that's 10 kilograms times 10 meters per second squared. So it's 100 newtons. What's another force that I have acting on it? The normal force, right. So I also have the normal force. All right, so I've labeled all the forces. Now I'm going to assign a coordinate system. Your coordinate system will almost always be obvious. Uh, that's going to be my y-axis. This will be my x-axis. Now I'm going to draw a free body diagram. You might actually decide to combine all three of these steps, or maybe even steps 1 through 4. But for now, I'm just going to do them separately. All right, so a free body diagram is just drawing those force vectors all on an axis. So I have one force here that's 20 newtons. That's at 30 degrees. I have one force here. This is my normal force. And then I have another force here that is 100 newtons. That's my weight. I want to know what that normal force is. I also want to know what is the acceleration of the block. Now, the next thing that I do, I've done this, now I need to do this step, find the x and y components. I only have one vector here that is not on axis, so it's really the only vector I need to be concerned about. And for your class, honestly, that's probably all you're ever going to find, is that you'll just have one vector that needs to be resolved into its components. Y'all can do that, of course, right? It's just 20 cosine 30, 20 sine 30. So I'm going to redraw this. Again, once you get good at this, you won't need to redraw it every time. But I have Fn. This is going to be 20 sine of 30, which is 10. This is 20 cosine of 30, which is what, 17 or something? Yeah, 17. And then I have 100 newtons. All right, so now I've resolved my vectors. Now I'm almost done. I really just have to write the equations. And remember Newton's second law, which says the sum of the forces equals ma. that this can also be applied in the three different directions. Right? I can say the sum of the forces in the x direction equals max, and the sum of the forces in the y direction equals may. Both of those are valid equations. And what we're doing now is we're just going to write a couple of equations, and we'll see where our unknowns are, and we'll just have to solve those equations. So now we're just to algebra, basically. All right, the sum of the forces in the x direction. How many forces do I have in the x direction here? I just have that one. I have that 17 newtons equals the mass times the acceleration in the x direction. And by the way, I also know the mass, right? It was 10 kilograms. So I can go and solve for this acceleration, because that's one of the things that I want to know. So let's just go ahead and do that, because we can. Just say 17 newtons equals 10 kilograms times the acceleration in the x direction. And so AX is equal to 1.7 meters per second squared. We don't know if it's moving in the y direction or not right now. It might be, right? If that guy's pulling hard enough, he could be pulling up that block off the floor. It's going to turn out that he's not, but we'll see that in just a second. Right, so in order to solve this, you divide both sides by 10, and 17 divided by 10 is 1.7. Okay, with me, folks? Okay, now we go to the next one. It's a little more complicated. I do the sum of the forces in the y. Look, I have two forces in the positive y and one force in the negative y. So I'm going to say 10 plus Fn minus 100 equals MAY. All right. Um, I know that this thing is not moving up because the 10, that's the force that the guy is pulling up with, is less than the weight of the object. So he's not applying enough force to make the object move upwards. By the way, if it was moving up, if it was moving up off of the ground, what would the normal force be? No. Remember, the normal force is a force that the surface is pushing up on the object with. So if the object is not on the surface, then what is the normal force? There is no normal force, right? So I know that this thing is not flying up in the y direction because this force, 10 newtons, is less than the 100 newtons. That should seem sort of intuitive, right? Like if this thing weighs a newton and I apply a force of a half newton, I'm not going to move it. It's not enough of a force. Is that intuitive for you? Okay. Well, no, I do have to solve each equation because I want to know what is AX. I've already gotten that, but I also want to know what is the normal force. You'll see why when we get to this. I don't think we're going to do it today, but we're going to get to friction, and friction is related to the normal force. And so you'll need to know that normal force in order to deal with friction, which we'll get to in class tomorrow. And if you're online, you might have already seen about friction. It's coming up. It's at the end of chapter 4. All right. So here, I know that AY is equal to 0. Listen, most of the time it's going to be 0, and usually I'll just say it. Shoot, practically all the time it's going to be 0, and I'll probably say that it's sliding across the ground, and then it's not moving in the y direction. And so in this case, MAY goes to 0. So I have 10 minus 100, that's negative 90, plus Fn equals 0. So Fn is equal to 90 newtons. All right. Notice that this normal force, 90 newtons, is less than the weight of the object. Look, if I have this thing and it's sitting on the table and it weighs a newton, it doesn't. But if it weighed a newton, it would have a weight that would be 1 newton. And the normal force would be exactly 1 newton. Okay? That's what scales do, right? They don't measure your weight. They measure your normal force. They measure the normal force that the scale is pushing back up on you with. They don't measure your weight at all. And it just so happens that your normal force is equal to the weight. Okay? Y'all look very excited to hear about this. All of you. Okay. All right. so that's a good 2D problem. If you look back at the old test, you'll find some samples like that. Yeah, yeah. Or in the y direction? Yeah, because you have the weight, right? You have the weight, the normal force, and because we had this extra force that was off to the side, it had a y component too. Yeah. You'll be dealing with 4 or more vectors on your free body diagram. All right, we had 4 vectors here total, including the x. Sometimes you'll also have vectors that are in this direction. Okie dokie. So what do I want to do next? Can we do an inclined plane? And you might not get all of it right away, and that's okay. But it's the first time that many of you have seen an inclined plane. So is that okay? Because you definitely have an inclined plane on your test. No doubt whatsoever. All right, so pretty typical problem. I have some object sitting on an incline. Let's say that it has a mass equal to 10 kilograms. For right now, we'll say there are no forces acting on it. There's no friction. There's nothing pulling up on it. It's just this object sitting on the incline. And I want to know a couple things. I want to know what is the normal force acting on this thing. And then I also want to know what is the acceleration. It's accelerating down that inclined plane, and I want to know what that acceleration is. All right. It's sitting. Yeah, I'm sorry. It's sitting right here. All right, but there's no friction. It's completely frictionless. So let's see. What our first step is to label all the forces. How many forces do I have acting on this thing? How many? Caleb? I just have 2, right? I have what? The weight and the normal force, right? So I have the normal force. Notice that I did not draw the normal force uh, opposite the weight, but I drew it perpendicular to the surface, because that's what normal is. It's perpendicular. All right. Oh, you need something else here. We need the angle of the incline. I'll say it's 30 degrees. Now I need to pick a coordinate system. Look, we could pick a coordinate system that looked like this. Don't draw that. Don't draw it. See, I can erase really easily. I could pick a coordinate system that looked like that, but we're not going to do that. This would work just fine with this problem, but when we get to more complicated problems, you're going to have all sorts of forces that are acting along the plane of the incline, and in that case, it will almost always be easier to draw your axes like this. So just get in the habit, whenever you're doing an inclined plane, that you'll draw your coordinate system like this, where your x-axis is acting along the inclined plane and your y-axis is up and down. This is also nice because when we go to find our acceleration, we'll only be looking for our acceleration in the x direction. Because I know this thing is going down that inclined plane. It's not flying off up in some other direction. But notice that if I had put this as my coordinate system, that I would have 2 components to my acceleration. My acceleration would be down this direction, and then I'd have both an AX and an AY. And it makes it a lot more complicated. All right. If you don't follow me, that's fine. Just always draw your coordinate system like that. All right. Did y'all know that I could do a pink dashed line? I don't think I've ever used that line before. I like it, huh? All right. So now we have labeled our forces. We've drawn our coordinate system. Now I'm going to draw a free body diagram. That's what I'm just going to go over here. I'm going to draw that coordinate system, and then I'm going to label the forces that are acting on it. Here's my Fn, and then I have my Fw. Okay, so now we need to pull out a little geometry. I need to know what is this angle. I'm going to call it theta. All right, I'm going to redraw this a little bit. Here's my triangle. Here's that force weight vector right here. And then this is going to be my y-axis, and this is my x-axis. So I'm just sort of pulling everything down to the incline. I know that this angle is 30 degrees, so what is this angle equal to? Huh? It's not going to be 30, no. It's going to be 60, because look what I got here. I have a right triangle. It's hiding in here. I have that right triangle, and I know that the angles of a right triangle add up to equal 180. I already have a 90-degree angle, so the remaining two angles have to add up to equal 90. So this angle right here is 60 degrees. Different books will do this differently. I recommend that you use that angle, that when you're finding the angle of the weight, that you use 90 minus the angle of the incline. You'll see why in a second, because it helps with your x and y components. You're not doing funky x and y components. You're still doing cosine and sine x and y components. Always measure your angle from the x-axis. That's good advice. Like I tell my kids, my biggest advice to them is don't go to jail. Like, that's very bad to go to jail. If you go to jail, I generally consider that you've made some major error in life. And uh, measure your angle from the x-axis. Okay, don't go to jail and measure your angle from the x-axis. Okay? All right. My brother is in jail once. He said it was the most miserable experience. He's just for a few days, but he said it was the most miserable experience that he's ever encountered in his entire life. Have y'all been in jail? No? Awesome. That's great. Okay, so where was I? Um, okay, so now we've labeled our forces. I know, by the way, that FW is 100 newtons. That's just 10 kilograms times 10 meters per second squared. And now I find the x and y components. So draw that again. I'm going to have 100 cosine 60 right here. 100 sine of 60 right here. By the way, this would be the same as 100 cosine of 30 and 100 sine of 30. So if you use this angle instead of 60, it would just flip-flop your x and y components. All right, because cosine 30 equals sine of 60. But don't sweat that. I'm just going to x that out. Okay? And then I also have the normal force, Fn. Now, I've found my x and y components. Now I write my sum of the forces in the x direction, sum of the forces in the y direction. I know in the y direction that this is equal to 0. In the x direction, it's equal to max. I just know that this block is moving in this direction, but it's not moving in that direction. It's accelerating in the x direction. All right? The sum of the forces in the x direction is going to be negative 100 cosine of 60 equals max. Sum of the forces in the y direction is going to be Fn minus 100 sine of 60, and that's all equal to 0. Okay? This is minus 50 divided by m, which was 10 kilograms, equals to ax. That's minus 5 meters per second squared. And then over here I have Fn equals 100 sine of 60. Sine of 60 is 0.86. So that's 87 newtons, or 86 newtons. You shall have a problem like that. We will see one complication to this where we will add in friction. So we'll add in a separate vector here that will be a frictional force. And we'll see that. Actually, I'll go ahead and introduce frictional forces right now. Okay. I know it seems like there's a lot of steps, but it's really just vectors, a little bit of Newton's second law, and then a little bit of algebra. Students often get hung up on that. Okay. And as you get practice with this, you won't need to take all these steps. You'll be able to combine steps. You'll be able to combine basically all 4 of these steps. And you'll just be able to look at it and just write Newton's second law, like, in your head. and solve it, and then just write the answer and do all the calculations. Okay, the 100 newtons here, right here, that 100 newtons. Okay, that was the force weight, which goes back to the mass of the block. So if the mass of the block is 10 kilograms, the force weight is that mass times g, which is 10 kilograms times 10 meters per second squared. That's where the 100 came from. That's really the only known force that you have. All right, good question. All right. This is sort of the hard part. The students get caught up on projectile motion and the inclined plane. All right. Let me introduce friction. We're going to talk about this in class tomorrow. Friction, we have two types of friction. We have static friction and we have kinetic friction. Static friction comes when objects are not moving. Right, they're static. And kinetic comes when they are moving. The frictional force in general is equal to something we call the coefficient of friction times the normal force. This is called the coefficient of friction. You measure it. Do we measure it in lab? Yeah, we do measure it in a couple of labs. We'll actually measure this when we get into energy. You do it experimentally. You do it experimentally by measuring the normal force and then measuring what the frictional force is, and then you just divide the two to get the coefficient. All right. Static friction has a coefficient that we typically call mu s, and kinetic friction is mu k. So these two are different. They're different in different situations. We'll talk about in class how they're different, but typically the static coefficient is bigger than the kinetic coefficient. That's why it's more difficult to get something moving, and then after you get it moving, it's easier to keep it moving. You ever done that? Moved a big heavy box across the floor? It's hard to get it started, but once you get it started, it's easier. It's because this static coefficient is bigger than the kinetic coefficient, almost always. So when we're talking about problems, let me go back. We're talking about problems like this right here. If you have this friction, it sort of throws a kink into it because the friction is equal to mu times the normal force. And so the normal force is located not only on the y-axis, but it is also on the x-axis. Or not that the normal force is acting on the x-axis, but there's going to be a normal force in your x equation. So when you get down to writing these equations, normally it looks all nice and pretty like this, but now you're going to throw a normal force there too. So you have more unknowns to solve for. All right? Which leads you to a system of two equations that you have to solve. All right. Let's work a simple problem. We'll revisit this problem right here. Let's see, we'll just sort of take this problem, 20 newtons, 10 kilograms. I'm going to go down a little bit. So I had a 10 kilogram block. This is the same problem. A force of 20 newtons. And the angle is what? Is it 30 degrees? Now let's say that the coefficient of kinetic friction hold on, let me go back and look. Is our normal force there? 90 newtons. Yeah, so we'll do our coefficient of kinetic friction is 0.1. All right. There are no units on that, by the way. It's just a number. I want to know how fast it's accelerating now. So this problem is same as we did it before, but it's just going to be a little bit different. So let's draw our forces on here. I know I have a normal force. I know I have a weight. That weight is 100 newtons. Again, 10 kilograms times 10 meters per second squared. And then I also have a frictional force. This is my kinetic friction, and it's equal to 0.1 times the normal force. All right, because I know that Fk is equal to mu k times the normal force. That's the Greek letter mu, by the way. It looks like an M, but it's a mu. It's sort of like a U with a tail on the left. All right. Okay, so now I draw my coordinate system. I've already done this, so I'm not going to spend a whole lot of time. Oh, wait. Awesome. All right, I'm going to do that in class tomorrow. Y'all wait. And y'all are all going to be ready for it. But the other students, they're just going to be blown away by the pink dashed line. Okay, so now I've drawn my coordinate system. I'm just going to sort of skip drawing a separate free body diagram. I'm going to go ahead and draw my x and y components here. So I have 20 cosine of 30 and 20 sine of 30. And I can draw in my Fn as well right there, just sort of reminding you. I have my Fk here, my Fw. All right. So now I've just resolved that vector onto its components, into its components. Then, y'all okay with that? We've already done that, so I didn't want to. Okay, now I'm going to write the sum of the forces in the x direction. Let's see, that's going to be 20 cosine of 30 minus Fk, which is 0.1 times the normal force. That's equal to 0. Or excuse me, that's equal to mass times acceleration in the x direction. And then I can also do the sum of the forces in the y direction. It's 20 sine of 30 plus Fn minus Fw equals 0. So if I want to now know the acceleration in the x direction, I have an unknown, and I have two unknowns in this equation. I don't know this, and I don't know this. So I have to solve this equation for Fn. So I say Fn equals Fw minus 20 sine of 30. Which one did we find that was? It's the same still, right? Oh, it was 90 newtons, right? 100 minus 10 equals 90 newtons. Y'all with me, folks? Or have I lost you? I sort of lost you a little bit, or just completely? Okay. Don't worry. If you're in the in-class section, we're going to get to it. Houston, you should be getting to it soon in the screencast. Okay, good. Awesome. Okay, so that's my normal force. And we'll wrap up with this. Now I can plug that in here. I'm going to have 20 cosine 30 minus 0.1 times 90 equals m. That was 10 kilograms times ax. And boom, I can solve that for ax. Point 1 times 90 is just 9. So over here I get 8.3 divided by 10 equals ax. It's 0.83. What did we get before on that problem when there was no friction? Don't remember. 1.7. So now we see, as you would expect, that the friction has slowed down this block. You're going to have 2 or 3 two-dimensional problems, okay? You have to be fast on them. Like, you have to not really think about them. So you just need to be able to sit down with them and just boom, 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 and just take all those steps. We've done them really slowly here, but once you get the hang of it, you know, you're going to have an inclined plane. You're probably going to have one like this with friction. That it's not going to be a mystery as to what's going to be on the test. But you just have to be fast to sort of make it through all the steps. But y'all can do that because you're smart and you're hardworking. All right, folks. Any questions? Last minute questions? All right, I think we'll stop there.